Welcome back, students. The topic for today's session is reactions of aldehydes and ketones. In my experience, I have found that students do not have much clarity on this topic even after learning. They understand when the reactions are explained in the class but have lot of difficulties in answering the questions in the examination. I want to make this session very useful to you by giving you some tips and practice in writing these reactions. Please sit with a notebook and pen. Now, aldehydes and ketones are called carbonyl compounds, you know. Aldehydes of formula RCHO and ketones of formula RCOR-, both have the carbonyl group, namely C double bond O. When you write the aldehyde this way, this is the carbonyl group, and the ketones have the carbonyl groups between two alkyl groups. So mainly the reactions of aldehydes and ketones are only reactions of the carbonyl group. We will classify the reactions into four groups: nucleophilic, addition reactions, then reactions with ammonia derivatives, though these also fall under nucleophilic addition reactions. We will have it as a separate category because there are quite a number of reactions to be learnt under this. Third, you have oxidation and reduction reactions. Fourth, aldol condensation and Cannizzaro reaction. I'll take them up one by one. Under nucleophilic addition reactions, there are four molecules that we are going to see how they add on to the aldehydes and ketones. Those are, in the first category, those are hydrogen cyanide, sodium bisulfite, Grignard reagent represented by RMGX, and fourth one, alcohols. Then what are nucleophilic addition reactions? Those are reactions in which whole molecules like hydrogen cyanide, sodium bisulfite or any of these compounds, whole molecules add on to the aldehydes or ketones across the carbonyl group. First, these adding molecules are polarized to form a negative part and a positive part. The first attack is made by the nucleophile, that is the negative part, on the positive carbon of the carbonyl group. I'll show you one by one in detail addition of hydrogen cyanide. Let me take up ethanol. I am going to write in one specific way which you should follow. That will make the job easy for you. See, this is the carbonyl group which is first polarized. The pi bond shifts towards the oxygen. So you have slightly negative oxygen and slightly positive carbon. Partial charges are created on carbon and oxygen. Then hydrogen cyanide is polarized to give H plus and Cn minus. Now it will be easy for you to add on. Then a nucleophile is the negatively charged part. So the cyanide group will first add on to the carbon, and then the positive hydrogen will join the oxygen. So this is the addition compound. HCN molecule as a whole has added on to the aldehyde across the carbonyl group by first the negative charge or nucleophile making an attack on the carbon, and then the other part joining the negative oxygen. These compounds generally called cyanohydrins. That is, any compound formed by addition of hydrogen cyanide to an aldehyde or a ketone is called a cyanohydrin. Now this hydrogen and this hydroxy group are attached to this carbon, so we can write it as CH3 CHOHCN. Can you give the IUPAC name of this compound? This is a 3-carbon compound and a nitrile. So it is propane nitrile. In propane nitrile, there is a OH group present on the second carbon atom. This is the first carbon atom and this is second. So it is 2-hydroxypropane nitrile. Okay, that is by the way. There is one more application of this reaction. This is all the reaction is. Nucleophilic addition reaction by hydrogen cyanide is only so much. But there is an interesting application of this reaction when you hydrolyze it. Hydrolysis here is reaction with very dilute acid where CN will be converted to COOH. It's a very common reaction that you should know because one of the reactions for getting carboxylic acid, hydrolysis of cyanides or nitriles. CN always on hydrolysis gives COOH. So this is a 2-hydroxy acid. 2-hydroxy acid that you get. So when you treat an aldehyde of formula CH3CHO, you end up getting CH3CHOH COOH. Here the reaction is addition of hydrogen cyanide to aldehyde followed by hydrolysis. Are you familiar with this compound? Does it look familiar to you? See here, if I write it this way, probably you will know. Sorry, I will show it this way. HOH CH3 COOH. This is called lactic acid having a chiral carbon atom. So we have come across this compound in optical activity. It is an optically active compound due to the presence of a chiral carbon here attached to 4 different groups. So this is nothing but 2-hydroxypropanoic acid, also known as lactic acid. This reaction will be very useful to you in conversion reactions also. Questions on conversion reactions. We are asked to give the question, convert ethanol to 2-hydroxypropanoic acid. It may appear very difficult. Ethanol with a which is a 2-carbon compound to 2-hydroxypropanoic acid. Unless you think of this reaction or learn this reaction well and keep it in mind that ethanol plus hydrogen cyanide, the addition compound that is formed on hydrolysis leads to this hydroxy acid. Unless you keep it in mind, this reaction will this conversion will appear to be very difficult, but it is a straightforward simple reaction involving 2 steps. Is that clear to you? Now, having learnt the addition of hydrogen cyanide on aldehyde, I want you to write the addition reaction of hydrogen cyanide on a ketone. I will just show you how to start. Now I want you to write it, do it on your own. So write the ketone like this. Keep the carbonyl group on the right hand side so that you easily add on the negative and positive groups here to write the equation. So please proceed and pause here, proceed and complete the reaction by yourself. Then come back and verify with what is given here. The answer would be CH3C CN, this is HCN, CH3 OH, cyanohydrin of propanone. Is that clear? Next we will see addition of sodium bisulfite. Sodium bisulfite or sodium hydrogen sulfite acts across the aldehyde or ketone as shown below. See here, show the polarization of the carbonyl group. Then show the positive and negative part of the adding molecule. It is Na plus HSO3 minus. And now you know which one should go where. It is CH3C, SO3H, and ONA. Now come on, try the same for propanone. Do it on your own and then come and check with the answer. These compounds are simply called sodium bisulfite addition compounds of aldehydes and ketones. They don't have a separate name. These are simply called sodium bisulfite addition compounds. These are white solids soluble in water. So this reaction has one very good application. When the aldehyde or the ketone is mixed with some non-carbonyl impurities. What are the non-carbonyl impurities? It can be an alcohol or acid or amine or any such compound which is not having a carbonyl group, reactive carbonyl group. In such cases, you can shake the carbonyl compound and take the carbonyl compound and shake it thoroughly with a saturated solution of sodium bisulfite. When you do that, you get a white solid. The white solid can be filtered and it can be treated with an acid. So when the bisulfite addition compound is treated with mineral acid, it regenerates the aldehyde and ketone. That is the reason for the usefulness of this reaction. These sodium bisulfite addition compounds, they regenerate the aldehyde or ketone on treatment with dilute mineral acid. So we will write usefulness of the reaction is in purification of aldehydes and ketones when these are mixed with non-carbonyl impurities. I can put the question this way. Propanone is mixed with a little methanol as impurity. How will you separate propanone or purify propanone? So what should you write? The propanone should be shaken thoroughly with a saturated solution of sodium bisulfite. The white solid that is obtained is filtered and treated with dilute mineral acid to get pure propanone. This is the way you should write the answer. Next we will take up the nucleophilic addition of Grignard reagent to aldehydes and ketones. All of you know Grignard reagent is a versatile compound having very wide applications. You can prepare large number of organic compounds having different functional groups using Grignard reagent. One of the reasons for the usefulness of Grignard reagent is the R can be of any size, starting from a small methyl group. It can be a large alkyl group with a large number of carbon atoms, with substituents, with unsaturation, and with even branched chains. So you can prepare any required organic compound by choosing a Grignard reagent with appropriate alkyl group. Now, I will show the addition of Grignard reagent to aldehydes. To begin with, I will take formaldehyde, which is the first member of the homologous series of aldehydes. For the Grignard reagent, I am going to take methyl magnesium bromide. We will polarize the C carbonyl group, creating partial positive charge on carbon and partial negative charge on oxygen. Now this Grignard reagent also gets polarized to form a negative alkyl group and a positive magnesium bromide. This is the peculiarity of the Grignard reagent. Normally, alkyl groups carry positive charge, but here the alkyl group carries a negative charge and you have a positive magnesium bromide ion. Now the positive adds on to the negative and negative adds on to the positive center. So we have here CH3H and MgBr. This is to be followed by hydrolysis. When you do that, a splitting of the bond occurs. Here it is MgBr. A splitting of the bond occurs between the oxygen and magnesium, with the hydrogen joining this side and OH group joining the other side of the bond. So what do you get here? H, C, H, CH3. This is OH plus Mg, OH, Br. See, this is the organic compound that you have obtained by nucleophilic addition of the Grignard reagent methyl magnesium bromide on formaldehyde. This hydrogen and the OH are all attached to this carbon. So I can rewrite it as CH3, CH2OH. This is magnesium hydroxybromide. This is another reason why Grignard reagent has been found to be so useful, because when you add Grignard reagent to any compound across the double or triple bond and then hydrolyze it, magnesium hydroxyhalide readily gets separated, leaving behind the organic compound. This compound is readily formed. That is why Grignard reagent is found to be so useful. Now look at this alcohol. You have two carbon atoms here. One carbon atom comes from this aldehyde and the other carbon atom comes from the alkyl group of the Grignard reagent. So the total number of carbon atoms will be found in the alcohol. And you get a primary alcohol from methanol or formaldehyde. Remember that. Now I will take the second member of the series, that is ethanol or acetaldehyde. And all of you know how to add do the addition. Now you can go ahead. Again I will take methyl magnesium bromide. So you can do it on your own now. You can write CH3, CH, CH3, O, Mg, Br, followed by hydrolysis, and the bond is broken here. The compound is CH3, CH3 here and H here, OH plus MgOH Br. Isn't it? Now what is this compound? When you rewrite the compound, this will become CHOH. So you get CH3, CHOH, CH3. Okay. So this is a secondary alcohol. Secondary alcohol. Look at the carbon atoms. This has 3 carbon atoms. There are 2 carbon atoms in the aldehyde. So 2 carbon atoms come from the aldehyde and 1 carbon atom comes from the alkyl group. So from methanol, when we did the nucleophilic addition of Grignard reagent, we got a primary alcohol. This is a primary alcohol. And when ethanol is added to Grignard reagent and hydrolyzed, you get a secondary alcohol. Keep it in mind. We will do an overall discussion at the end of the reaction. Next compound for consideration is propanone. Propanone. We will take this time ethyl magnesium iodide. Okay, so this is the negative part, this is the positive part, and here you know this is negative and this is positive. Please complete the reaction. When it is hydrolyzed, so here you get OMgI. The compound when you rewrite is COH plus MgOHI. This is a tertiary alcohol. You can check the number of carbon atoms. Here it is 1, 2, 3 and 2 here 5. You have 1, 2, 3 plus 2 here 5. So the number of carbon atoms is the total that we get from the 2 compounds. And you get a tertiary alcohol from a ketone. So we can make a generalization now. Formaldehyde plus Grignard reagent followed by hydrolysis gives you primary alcohol. So it depends the compound that you obtain. It's all primary alcohols, but which compound you get depends on the Grignard reagent that you choose. When you take any other aldehyde, so I will write the general formula RCHO. It need not be ethanol. It can be any aldehyde other than methanol with Grignard reagent followed by hydrolysis. You get secondary alcohol. And a ketone or CO or dash of formula with Grignard reagent followed by hydrolysis gives you a tertiary alcohol. So if you understand the reactions clearly and keep this in mind, you will be able to do conversions very easily. I will give you some examples now. For the conversion reactions now, I will give you some tips. If you take formaldehyde and then a Grignard reagent C2H5MgBr followed by hydrolysis, you can straight away write the compound without going through the steps of charge creation, addition, etc. I will tell you how. Here for the product, first write the alkyl group from the Grignard reagent and a CH2OH from the formaldehyde. Is that clear? The formaldehyde supplies a primary alcoholic group and then the alkyl groups comes from the Grignard reagent. Is that clear? This is how you have to write when a Grignard reagent is adding on to the formaldehyde by nucleophilic addition and followed by hydrolysis. Now when I take say CH3, CH2, CHO, propanal plus, I am taking the Grignard reagent. Okay, let me write once again C2H5MgI subjected to hydrolysis. What would be the product? Because it is an aldehyde other than methanol, it should be a secondary alcohol, isn't it? So secondary alcohol will be just this, where CHO is converted to CHOH, and the alkyl group from the Grignard reagent must be added here. Here remember C2H5 is CH3CH2, isn't it? So when you add on here, the carbon where the bond is broken must be joined here. So it should be CH2CH3. So what is the name of this compound? It is 1, 2, 3, 4, 5. It is a pentane compound. It is 3-hydroxypentane. Is that clear? For the third one, I am going to take butanone. CH3CO, CH2, CH3. And I am going to add isopropyl magnesium chloride. Okay, it is isopropyl magnesium chloride because the MgCl is joined to the middle carbon atom. Otherwise it would be propyl magnesium chloride. This is isopropyl magnesium chloride followed by hydrolysis. Now pause here and try to write the compound, the product if you can, and then you can check with the solution here. Pause here, go ahead and do that. The product is CH3, C, remember the ketone becomes the tertiary alcohol. So I will put the OH group below, and it is to this carbon atom that the alkyl group from the Grignard reagent is going to join. Here it was not difficult for you because the CHO is at the end of the molecule and you could just make it CHOH and continue writing the alkyl group from the Grignard reagent. But this is a tertiary alcohol, this is a ketone where this carbon itself is connected to two alkyl groups. So you must be very careful in writing the product here. So this is the tertiary alcohol that you get, and this is the carbon to which the alkyl group of the Grignard reagent joins, and here this carbon loses a bond, so it is this carbon which should be joined here, and this carbon is already connected to two methyl groups. Is that clear? Does it look very complicated? I have particularly chosen this to explain all the aspects of the reaction. See, here I have taken a ketone for addition by Grignard reagent, and this Grignard reagent is isopropyl magnesium chloride. When this is subjected to hydrolysis, the ketone group is going to provide a tertiary alcoholic group. This ketonic carbon is already carrying two alkyl groups. One is the methyl group, the other one is the ethyl group. So we have shown them here, and the C becomes COH. And then it still has only three valencies, isn't it? The fourth valency is satisfied by the alkyl group that is joining the carbon, and the alkyl group again has a branch there. So the carbon which is undergoing the bond breaking, that is the one which is to be joined to the carbon here. So this CH is here and it is carrying two methyl groups which are shown. So this is the product that you get. You can try writing that writing the IUPAC name of this compound. See if you can complete the given two equations and write the main compound formed. Please pause here, write it in a notebook and then check with what I give on the board here. You can verify your answers now. In the aldehyde, the CHO becomes CHOH, and then the ethyl group of the Grignard reagent, when it is joined there, must be carefully written as CH2CH3. The common mistake would be to write it as CH3CH2. If you write it as C2H5OH, the C2H5 is okay, but you must be careful while writing the IUPAC name. You must count the two carbon atoms. Or if you are spreading it out, it should be CH2CH3 and not CH3CH2. In the case of the ketone, the CO becomes COH. So push the methyl group up so that you are able to join the alkyl group from the Grignard reagent. The two alkyl groups of the carbonyl carbon must be arranged carefully, and then the alkyl group C2H5 is joined here as CH2CH3. What is the IUPAC name of this compound? If you have written it correctly, it should be 2-methyl pentane 3-ol, and this one is 3-methyl pentane 3-ol. Is that clear? So go over these reactions once again and understand the reactions well. The fourth and the last compound in this set is alcohol. Let us see how alcohol undergoes nucleophilic addition reaction with aldehydes and ketones. Let me take a general aldehyde RCHO and take the alcohol R-OH. This reaction takes place in the presence of dry hydrogen chloride. You should remember that. Now, do the usual polarization of the carbonyl group. So, you get R, C, O with a positive charge on the carbon, the negative charge on the oxygen. Now, the alcohol polarizes in such a way that OR becomes the negative part and H becomes the positive part. So, the H will add on to the negative oxygen and OR dash will add on to the positive carbon. This is the product you get, and this is called hemiacetal. This is the hemiacetal of the aldehyde we have taken. This is an alkoxy group or ether group. This is an alcoholic group. So you can call it alkoxy alcohol. This is an alkoxy alcohol. This reacts with one more molecule of the alcohol. When it reacts, a molecule of water will be eliminated and this OR dash attaches itself to this carbon. So the product will be RC OR dash H and OR dash. This is called acetal. This is the complete reaction. This is called acetal. It is a dialkoxy compound. Is that clear? So an aldehyde reacts with an alcohol in the presence of dry hydrogen chloride. It undergoes the usual nucleophilic addition in the same way that you have done for earlier compounds. The positive hydrogen joins the negative oxygen and the negative OR dash joins the carbon to form a hemiacetal or alkoxy alcohol. This reacts with one more molecule of alcohol to form a dialkoxy compound which is called acetal. This is the general reaction I have given. For practice, you do for this specific compound. I am giving you ethanol or acetaldehyde plus methanol in the presence of dry hydrogen chloride. Please pause here, go ahead and complete the reaction and write both the products. Write both steps of the reaction and write the products. The product is this hemiacetal First product is this hemiacetal, and then this reacts with one more molecule of methanol to form the acetal. Hope you had no difficulty in writing the products. Now we proceed to the reaction with ketone. For ketone, I will take propanone. This reacts with a dihydric alcohol, namely glycol or ethane diol, in the presence of dihydrogen chloride, and it forms a cyclic compound like this, which is called ketal. This forms a cyclic compound called ketal. So here the alcohol reactions, I suppose you have understood. Ketone reacts with dihydric alcohol with the dihydrogen chloride to form a cyclic ketal. Now see the questions on the board. These are the follow-up questions on the nucleophilic addition reactions of the 4 compounds that we have studied. Try to write the answers on your own, then come back and see the solution. I am giving you the solution now. First one is methyl hemiacetal of formaldehyde. So take formaldehyde, show the charge creation, take methanol, that is because it's given methyl hemiacetal, so you have to take methanol. Right? Don't forget to write the dry hydrogen chloride there. The aldehyde given is formaldehyde, so we have taken that, and this becomes OH. The H part will go here and the methoxy part will go to the carbon, so you get methoxy hemiacetal. You are asked to write only the structure of hemiacetal, so this is the compound. Since you are asked only the structure, it's enough if you write that. So for clarity, I have shown the entire reaction. There is no problem in writing the entire reaction. You can write it as the answer also, because only by doing so you can arrive at the product. But it's enough if you do it as a rough work and show only the structure of hemiacetal for this question. The structure of B is this: dimethyl hemiacetal, which is obtained by the reaction between acetaldehyde and methanol in 2 steps. I suppose you could do that. Now, the first one in the conversion reactions is methanol, that is formaldehyde, to be converted to butane 1-ol, that is CH3, CH2, CH2, CH2OH. You are given an aldehyde and you are asked to obtain a primary alcohol. Normally, an aldehyde to alcohol reaction is a reduction reaction. You can use a reducing agent like hydrogen in the presence of a catalyst. It would give you an alcohol, primary alcohol. But when you reduce methanol, which is a 1-carbon compound, on reduction it will give you only a 1-carbon primary alcohol. That is, you will be getting methanol. But you need butane 1-ol, which is a primary alcohol with 4 carbon atoms. This has 1 carbon atom. Now it should occur to you that you have to use Grignard reagent. So when you use Grignard reagent for this reaction, you must know that the other 3 carbon atoms must come from the Grignard reagent. So you can choose your Grignard reagent like this. It is propyl magnesium bromide. And then when you do the hydrolysis, you can straight away write the product as butane 1-ol. So if you have understood all these nucleophilic addition reactions, this should not be a problem for you. Once you practice such a reaction, it will occur to you when you meet such questions in the question paper. The second one is ethanol to propanone. Ethanol is CH3CHO. Ethanol to propanone. Here you have to do a little thinking. This is an aldehyde with 2 carbon atoms and you have to get a ketone with 3 carbon atoms. I will show it here. Here also we are going to use Grignard reagent because you know an aldehyde reacts with Grignard reagent followed by hydrolysis gives you a secondary alcohol, isn't it? Ethanol gives you a secondary alcohol. So I am going to take it here, methyl magnesium bromide followed by hydrolysis. Can you write the alcohol at least know which alcohol? It is CH3CHOH, the secondary alcoholic group coming from the aldehyde, and the alkyl group from the Grignard reagent. So you are getting propan-2-ol. Propan-2-ol, it's a secondary alcohol. And what do we need to get? We need to get propanone, isn't it? Propanone. Secondary alcohol to propanone, you know, is oxidation. So here we will use a mild oxidizing agent, or we will use the reaction passing over copper at 573. You can write here copper at 573 Kelvin, or a mild oxidizing agent like chromic oxide will oxidize the secondary alcohol group to ketone. So you are getting here propanone. So this is the way you have to bring about the conversion of ethanol to propanone. This will be a good conversion for you to practice. I suppose you are having clear idea about the nucleophilic addition reactions of aldehydes and ketones. The other reactions we will take up in following sessions. Thank you.